Bismillahirrahmanirrahim. Extrinsic semiconductors are materials that have been doped with specific impurity to enhance their electrical properties. This modification allows them to conduct electricity more effectively than intrinsic semiconductors, which are pure and have limited conductivity. The doping process introduces free charge carriers, either electron or hole, depending on the type of dopant used. Extrinsic semiconductor can be classified based on the type of dopant used as N-type semiconductor or P-type semiconductor. In N-type semiconductors, which are created by doping with elements that have more valence electrons than the semiconductor material itself. For example, silicon, which has a 4 valence electron, if we add some impurity which has a 5 valence electron, then this doping will create N-type silicon. Most common element from group 5A as phosphorus, arsenic, and antimony are commonly used N-type doping. Also refer as a donor for P for N-type. Because the dopant atom provide extra electron which become free charge carriers, thus increasing the number of negative charge carriers. The excess electrons are responsible for electrical conductivity. Now we discuss about p-type semiconductor. P-type semiconductor are formed by doping with elements that have fewer valence electrons than the semiconductor. The most common element from third A group, such as boron, aluminium, and gallium, are the typical p-type dopants, also referred as acceptor for silicon. The introduction of these dopants create hole in the semiconductor valence band, which act as a positive charge carriers. The movement of these holes facilitate some electrical conduction under the influence of applied voltage. The control of conductivity, which is very crucial for the design of any electronic devices, it depends on the concentration of dependent concentration of dopants. The concentration of dopants directly affects the electrical conductivity of the semiconductor, as discussed in earlier unit. Higher concentration results in more free carriers, enhancing conductivity, and at that moment, we introduce the concept of compensating doping. In some cases, both N-type and P-type dopants are introduced to achieve specific electrical characteristic, balancing the charge carrier. We will discuss in detail after a few minutes. There are several methods are employed to introduce the doping into semiconductor. Some process such as diffusion. Diffusion involves exposing the semiconductor to a gas or solid source of dopant at very high temperature, allowing the dopant to diffuse into the material. The depth of the dopant penetration can be controlled by adjusting the temperature as well as process time. Another technique is ion implantation. In this process, dopants ions are accelerated and implanted into the semiconductor substrate. Ion implantation allow for very precise control over the concentration and depth of doping as compared to diffusion process. And and making it is a popular choice in modern semiconductor industries. Another technique for doping is molecular beam epitaxy. Molecular beam epitaxy is a technique used to grow thin film of semiconductor while introducing dopant at the atomic. This method is often used in the fabrication of advanced semiconductor process, and relatively MB is much costly as compared to the previous technique. Now we discuss about the electrical properties of extrinsic semiconductors. And the most important electrical properties we discuss is conductivity. Extrinsic semiconductor exhibit significantly higher conductivity than intrinsic semiconductor due to the presence of free charge gap. Another important electrical parameter is mobility. The type and concentration of dropants generally affect the mobility of charge carriers, impacting the overall performance of semiconductors. Another important parameter is temperature dependence. The availability of extrinsic semiconductor can vary with temperature, affecting their conductivity and the energy required for the conduction process. Application of extrinsic semiconductors are mostly used for diode transistors. Extrinsic semiconductors are essential in the fabrication of bipolar junction transistors, field effect transistors, which are critical components in modern microelectronic industry. Particularly diode PN junction is formed by combining N-type and P-type semiconductors are fundamental in diode operation, enabling functionalities like rectification and signal modulation. Similarly, solar cells, extrinsic semiconductors are also used in photovoltaic devices to improve light absorption and charge carrier separation, enhancing energy conversion efficiently. There are some challenges for the doping mechanism for doping process for semiconductor, and one of the most important challenge is contamination. Uncontrolled doping can lead to the contamination, affecting the performance and reliability of semiconductor device. Another important challenge is heat treatment. Post-dropping annealing process are often necessary to activate dopants and repair damage to the crystal structure generally induced by the dopant into the semiconductor thin film or substrate. And another important challenge is material compatibility. The choice of dopant must consider the compatibility with the semiconductor material and the desired electrical characteristics. Now we discuss about compensated doping. As we have discussed that compensated doping refers to a technique used in semiconductor physics where both donor, maybe N-type and P-type impurities are added to the material at the same time. The purpose of this method is to control the electrical properties of semiconductor, typically trying to achieve a desired level of conductivity while maintaining specific characteristics of material. Thank you.